we're good.
Right, fantastic. So welcome everyone to the Data Science Institute lunchtime talks. By the power of, I almost said Grayskull, I'm showing my age. By the power of internet, we're able to bring you not one but two speakers today, and I was privileged enough to be part of a session with them with some computational biologists where they were looking really at the fact that we're using AI and NLP for everything, and there were growing computational impacts, and both our speakers today are concerned with that, and I don't want to steal their thunder too much, but I'm delighted to have them both here. So Roy Schwatz is assistant professor at the Hebrew University of Jerusalem, and he has a background firmly in AI at UW and postdoc experience. And I notice that his work on this subject has been picked up in the major media, and while he's talking, I'll probably post some links so you can follow up on that. And Loic is finishing his PhD at the Department of Public Health and Primary Care at Cambridge. And I think, is it fair to say that this is almost the sort of sideline you've got going on to your PhD about the impacts of AI, but you've been sort of working on the Green Algorithms project, and there's a really nice tool that I'm sure you'll mention. Okay, so we've got about an hour. We're going to fit two talks in. Roy's volunteered to go first. So Roy, I'm sure you'll keep to time, but I'll just put something in the chat if you're getting close to the end of your 25 minutes, and then we'll have time for questions. So please share your screen and begin when you're ready.
Okay, can you see my full screen now? Adrian, someone, can you see my screen?
Yeah.
Yes.
Sorry, I did a thumbs up. I should have said yes. I can see that, but actually we're seeing the not the presenter view. We're seeing with the slides down the side.
That was my concern. So I'll share the entire screens. I think that should be fine. Now?
That's perfect. Yeah, that's perfect.
Great. Okay. So hi everyone. Thank you so much first for inviting me here. I'm really delighted to be here. So my name is Roy Schwatz, and I'll be telling you today about Green AI. So before I get started, just a few words about myself. So I'm a senior lecturer at the School of Computer Science at the Hebrew University of Jerusalem, and I study artificial intelligence and more specifically NLP. And my main research areas are understanding AI and NLP models, revealing the biases in those in datasets that we use to train and test our models. And the topic of this talk is ways to make AI more sustainable. So when we think about AI today, we've seen tremendous breakthroughs in areas such as machine translation or game playing or identifying objects or faces within images and so on. And of course, even within the current challenge of society or humanity of COVID, we've seen AI at the front helping researchers and develop both vaccines and medications. And something that perhaps is a bit less noticed about AI models is that they're becoming bigger and bigger. So what we're seeing here is a graph plotting the state-of-the-art AI models between 2012 and 2018. And on the y-axis, we see the amount of computation used to train these models. And we see an exponential growth of about 300,000x in 6 years. And this obviously hasn't stopped in 2018, but has continued to grow. And while this growth has led to tremendous success and tremendous breakthroughs in various areas of AI, it also creates several concerns that I'm going to be briefly talking about. The first concern is about inclusiveness. When models become bigger and bigger, fewer and fewer organizations and researchers can afford to play with them, to train them, to use them. And indeed, if you look at this graph that shows a very similar plot to what we've seen earlier, just in NLP, the growth in parameters of state-of-the-art models in the past few years, you see that basically, almost all of these works are done in huge companies such as Google, Microsoft, Facebook, and so on. which leaves people like ourselves here in academia the position that we're really unable to participate in this quote-unquote game of chasing the state of the art. And even if you don't just consider the research community, but go beyond that to the community of people that use AI, and these models are becoming so big and with so many parameters that they can't be deployed in real-life applications. So a question might arise whether we're building this technology for the fun of it, or are we actually doing something that other people can use? And finally, most related to this talk, we've started seeing as models become bigger and bigger that they are becoming environmentally impactful, and not in a good way, unfortunately. This is a slide from Emma Struppel's paper a few years back that studied the carbon footprint of NLP models. And one of her key findings was that training a transformer model with a neural architecture search consumes the same amount of CO2 as 5 cars would in the course of their lifetimes. So thinking about all these problems together, I missed this slide. When we think about AI in the environment, the evidence that we have with respect to Emma's paper or a few other follow-up papers is about the most expensive experiments. These are typically run very few times by, again, very rich companies. And we know that about their environmental impact. But what about normal experiments? Those that are run, maybe they are much cheaper, but they're run way more frequently by hundreds or even thousands of researchers per day. And even more so, what about inference operations? Those that are really cheap, they don't cost much money, but these can be run billions of times a day. Think of the amount of Google queries or Facebook posts or Amazon searches that people run over in the course of a day. And indeed, there are some estimates that 80 to 90% of AI computation is spent on inference. So I think that the key challenge that I will be addressing later in this talk is how do we measure the carbon footprint of AI in the environment? So to address these problems, we, myself and colleagues at the Allen Institute for AI, released a position paper called Green AI a couple of years back. And in that, we defined the term red AI, which talked about increasing AI simply by making it bigger and more expensive, and talked about the problems that I just mentioned about inclusiveness, adoption, and the environment. And we proposed an alternative or another way to move forward, which we called Green AI, and where we focused on two main avenues to pursue. One is to do enhanced reporting of computational budgets, basically add some price tag to every scientific result. And the other is to promote efficiency as a core evaluation to AI, in addition to accuracy. Now, in this talk, I will talk briefly about each of these two lines. But before I get started, I want to highlight an important point about big and expensive models, and that I'm not advocating to eliminate these models. I think they have a lot of value in pushing the limits of state of the art. And ironically, in many cases, releasing large pre-trained models helps save compute because it saves other people from running the same experiments. And there's also evidence that large models are potentially faster to train compared to smaller models. However, as we've talked so far, big models have concerning side effects relating to inclusiveness, adoption, and the environment. And our goal is to mitigate these side effects. And this is what I'm going to try to convince you that we want to do. So a brief outline of this talk. I'm gonna again focus on the two avenues that we propose to push forward. One is to do enhanced reporting, and the other to focus on efficient methods for AI. In each of these, I will briefly discuss some existing work, and then also quite briefly, unfortunately, due to the interest of time, touch on some of my own work relating to this, and I will finish with some ways forward and open questions that I think are interesting in both of these areas. So let's begin with the first topic of enhanced reporting. And I want to start with a nice example from a paper by Reimers and Gurevich from 2017, which illustrated the point that I want to make very clearly. So consider a typical AI paper where we have the authors propose a model, let's call it model A, that gets that they argue that it does a better job on some task compared to some baseline, let's call it model B. And the way they do it is to report higher numbers on some measure, say F1. And in this case, we can imagine the authors of model A publishing this paper and providing this as evidence. So Ribas and Gurevich were wondering whether this single number experiments represents the true quality of these models. And what they did is to reproduce these experiments multiple times. And what you see here on the right-hand side is our histograms of different experiments with the blue model and the green model. And as you can, and higher is better on the scale of F1. And as you can see, this graph tells a very different story than the single number table. And the mass of the mass of the green part is much higher than the one of the blue part, and it's also more concentrated, so with lower variance. So we might, if we had to choose between these two models, we would actually prefer model B over model A. And this brings a question that when we're just comparing whether model A is better than model B, are we asking a fair question, or are we making a fair comparison? And maybe what we want to ask is whether model A is better than model B under some budget constraint. And let me provide some intuition or some details about what we mean by that. So in a paper that we published in 2018 with, again, colleagues from the University of Washington and the Allen Institute for AI, we proposed a method called a measure called expected validation performance. And the key idea is that if our input is a set of experimental results, say V1 through Vn, and the typical way to present results is just to take the maximum of them and compare it to the maximum result of our baseline. But we want to consider what happened if we had a smaller budget of size k that is smaller than n. And so basically, when we run our experiments and produce some result in a given paper, we have our own budget, say n, but someone might want to take these results and reproduce them in a setup where they have a smaller budget. And can we count on our results to translate to these smaller numbers? So this is the problem we were facing in this work. And our solution was to define something called expected validation accuracy. And intuitively, what we're talking about is the expected max value of selecting k values out of these n values. So basically, if we wanted to know what's the expected number that we're going to get if k equals 1, we would simply take the maximum value of between these n numbers. But if we wanted k equals 2 or 3, we will take all the pairs or triplets out of n and compute the average maximum values of each of them. And this provides us with something that looks like this. We have on the x, we can generate a plot that on the x-axis we see what is our budget, in this case hyperparameter assignment. So going to the right, we have a higher budget. So as we expect our expected validation accuracy to go up. And again, the y-axis is our measure. And what this allows us to do is to come up with a nice experiment like the one we see here, where we compared two methods on logistic regression and CNN classifier on a task of sentiment analysis, so with the SST5 dataset. So we can see that if we have a low budget of about 10 or until up to 10 or 12 hyperparameter assignment, we find that the logistic regression outperforms the CNN. So the conclusion that we will make if we had a small budget is that we should favor the logistic regression. However, once we go into the higher budget areas, we find actually the CNN is better than logistic regression. And this tells us in a really nice way that asking whether model A is better than model B is not a well-defined question. You have to take into account what is the computational budget that we have in hand. And in this case, given this budget, we might reach different results based on the amount of computation we have available. So when we talk about reporting, we can think about various open questions that are worth asking. One is how much will we gain by pouring more compute? The results that I've shown you allow us to take our results that say we ran 50 experiments, and now we want to imagine what happened if we had less computation. But maybe potentially even more interesting question is can we extrapolate guess how will we do if we had more computation? This is a very interesting open question, and we've started seeing some interesting results recently. The second question is, what should we report as our computational budget? Should we control for the number of experiments, the amount of training time or inference time, the amount of floating point operation, the amount of energy, the amount of carbon? Each of these measures is important on its own, and perhaps it depends on the application, but it's definitely worthwhile considering ways to measure each of them and combining these measures together. Okay, so we've talked a little bit about intense reporting. We've talked about the motivation behind it, some ways to make progress on it, and some open questions. And now I want to move to the second part of the talk, which is efficient methods for AI. So the motivation to working on efficiency is that basically most AI, nowadays, most AI authors care more about accuracy than efficiency. To illustrate that, we took, in our Green AI paper, we compared, we sampled 20 papers for each of 3 top AI conferences in the years 2018 and 2019, and we considered whether their main scientific claim talks about increased accuracy on red, increased efficiency on green, or either both on yellow or some other contribution on blue. And we see that in all 3 cases, many more papers focused on accuracy compared to those focusing on efficiency. And we think that this trend doesn't necessarily reflect the value to the community, and we think that these graphs should be a little more balanced. You need to see more works working on efficiency and not only focusing on accuracy. So when we think about efficiency, there are several questions we need to be asking ourselves that also relates to the previous question of measuring. We want to ask what is it that we're trying to make more efficient? And we can think about different stages in the life cycle of an AI model, whether it's the process of model selection. We have multiple potential models, then we want to select the best one, as in the case of hyperparameter tuning. Whether we want to make training more efficient by making the training process faster or consume less energy, or perhaps inference that, as I've shown earlier, contributes most to the carbon footprint of AI. And again, when we think about efficiency, we also need to ask ourselves, what exactly are we measuring? How do we know that something is more efficient? Whether we want to make it more faster, basically save time, save energy or carbon, or save space, the number of parameters that the models are using. So in the next slides, I will present several different works my lab has done in the last couple of years that present several solutions to making various aspects of AI more efficient. The first idea is an idea of how to make efficient inference. And here the idea is that we want to identify easy instances at inference time and allow the models to invest less compute in those instances in order to save runtime and energy. So to illustrate this, consider this, say we have a model with n layers, each of these layers adding another level of computation. So what we would do is, and typically add a classifier to the final layer. We would run each input all the way through the layers, each of them, again, adding some level of computation. And then we would run a classifier that would give us the prediction of the model. And the key intuition is that maybe we don't have to run all of these layers in order to reach an accurate prediction on some inputs. So to illustrate this, what we would do is we add a classifier not only in the final layer, but also in previous layers. So say here close to the layer 0. We will start by making a prediction and ask the model whether it is confident enough. If it is confident enough, we would make an early exit, and we've saved almost all of the computation of the model in a very simple way. If it's not confident enough, we can continue to our next classifier, which comes say at layer 2, and repeat this process of making a prediction, asking whether it's confident. If it is, make an early exit. If not, move on all the way, and in the worst case, we would reach the final layer and make a prediction there. So again, this idea allows us to, on average, save a lot of compute, because on many of the instances, we can afford to make an early exit much faster, much earlier, and accordingly much faster. And indeed, our experiments show a speed up inference by a factor of about 5 on some of our datasets. So this is the first work. The second work talks about how to do training more efficient, in particular more data efficient. And the key idea here, this is a joint work with colleagues at the University of Washington and the Allen Institute for AI, published at the MNLP last year. And the key idea here is that we want to identify different regions in the data. And when we identify them, we find that many of them contains mostly easy examples, which do not contribute much to training. And because we can identify these easy instances, we can afford to not to train on many of them. And so the overall training phase would be much shorter because we iterate over much fewer examples. So our method allows us to build this map here on the right, where we divide the data set where each of the points in this map corresponds to a different training instance. And we can see that this map creates different regions that I won't go into too many details, but the top left-hand area corresponds to instances that are easy to learn by the model. And you see this area is much more dense. So we can afford to, when we do training, to avoid training on many of these instances. And as a result, focus more on the two other regions of instances we call ambiguous and those that are hard to learn. So again, and I won't go into too many details, but I hope you got the intuition. And again, when we train these models, train several models on instances from those regions that are most valuable, we get a speed up of training of about a factor of 3. So basically, we can save 2/3 of the data, not train on it at all, and get roughly the same result, but much faster. And another similar idea talks about making efficient multi-model pre-training. This is joint work with researchers here at the University at Ben-Gurion University, published at the Findings of EMNLP last year. And here the idea, the task that we're focusing on is vision and language pre-training. So if we have this image here of a person feeding a carrot to a tiger, then the basic procedure is to take the caption describing this sentence and mask some of the words randomly. So we might get something like a tiger mask eating the carrot, which, as you can imagine, the mask word is. And what we do in this work is we find that when we carefully select which words to mask, we reach much better efficiency because we're able to make much better usage of our models. So for example, our method, instead of masking the word is, which is probably doesn't provide much information to the model, we would mask, for example, the word tiger. Now this allows us to do substantial speed up of vision and language pre-training by roughly 2-fold. And finally, a very different work that talks about efficiency talked about the transformer model, which I assume most of you have heard of. And what we do in this work is we propose a mathematically efficient alternative to transformers. And the key idea is to replace softmax attention with random feature attention. So what do I mean by that? If we see here on the figure the standard softmax attention, you can see that, I'm not sure if you can see my cursor, I can't see it either, so I'll just use I'll describe it in words. We have an operation between the queries and the keys that result in a quadratic complexity of running the softmax attention operation. And what we do is we replace this softmax with a process called random feature attention that allows us to run this procedure in a linear time instead of quadratic time, while getting a very close approximation of the original softmax attention operation. And the results we get is a substantial speed up in both training and inference, and a reduction in the parameter overhead. Okay, so I've presented several different avenues to tackle efficiency. These are obviously just a few of my works, and there are obviously very many different other methods to do efficient work in AI and NLP. But here are a few open questions that I think are worth considering by the community. The first is tackling sample efficiency, basically finding ways to make training more efficient. The second, what makes a good sparse structure? Can we identify models that are sparse in terms of parameters, can we identify these structures to begin with and characterize them in a way that allows us to train a sparse model from scratch. And I think another very interesting question is what makes a good hyperparameter or random seed? Can we know in advance, without running multiple experiments and choosing the best one, can we identify them in advance? Okay, so to conclude, we've talked about Red AI as something that's the practice of just improving AI by making things bigger and more expensive. And we presented Green AI as an alternative for that, where we focus on enhanced reporting of computational budgets and of more efficient methods. So I hope you've enjoyed this talk, and thank you for your attention. I'm happy to take questions.
Wow, that's really perfectly kept time, Roy. A beautifully structured talk. Thank you so much. So if people want to raise their hand in Teams, I can see people virtually clapping. That's I know if you're in the room, there'll be real clapping. So don't worry about that. If people would like to raise their hands or post in the chat, I'll bring people in for questions. So I'm just going to keep an eye out for that. I
can only see my screen, so I can't see the chat or anything. So
yeah, no, okay, that's totally fine. So while people are thinking about that, so one thing it always. So I'm old enough to remember punch cards, right? Where computation was so expensive, people had to do a lot of work to go and even do computation. And then as it's got cheaper, people do more and more redundant compute. You just keep hitting compile and hoping the bugs will fix themselves, or you keep training the model. Do you have a sense, or does the community have a sense for how much energy is spent on, picking parameters or models that never get to be trained in the first place? Is there like an iceberg here of a lot of wasted computation?
Yeah, that's a very good question. I think it's one of the key points in my study is how hard it is to measure things, and I think this is a great example of how it is hard to measure. I mean, we had an initiative while I was working at AI2 a couple of years back of trying to convince or to promote people reporting the amount of computation used throughout the life cycle of a project. So let's say, which is not even very well defined, but let's say you start a project on day one, which you kind of know what it is, and kind of you run a bunch of experiments until you converge on your method, and then you run more experiments. So ideally, we would like to have again, I use the term price tag that tells you how much the current research idea or the research result costs. Again, cost in terms of money or computation or electricity or whatever. And this has been hard to push because most people don't keep track of all this information, but we're still trying to develop basically technological tools that will allow to measure this in a more reliable way. But I don't have any concrete results yet, unfortunately.
No, I like that suggestion. I know some colleagues working on a project called Paris D, where they're trying to track their end-to-end carbon footprint as a project in a similar way, and that's part of the work plan of the project. So, maybe what you're sort of hinting at is better accounting for the work we're doing as kind of scientists, and more transparency around that, which I quite like. So, Damien, you put your hand up. Would you like to come in with a question?
Sure. Hi there, and thanks for your talk, Roy. It was really interesting. I actually used your work, especially the green AI, as kind of an inspiration for my own research. So it's really cool to listen about your work. My question is very specific about one of the slides that you've shown, which was the inference speed up, as to how you use different, the one with the layers, rather.
This one?
Yes, this one. So I'm just curious about how I'm kind of thinking about a regular deep learning model with layers. Each of them have a different output, and in this case, how do you determine confidence at each of the layers? What would be the kind of signal to say that we're quite confident at this point?
Yeah, that's a great question. So if you see, these layers feed each other, right? So you have, if we didn't have, in a standard model, you have layer 0 feeding layer 1, which feeds layer 2, and so on until layer n. where you would add a classifier on top of it, doing some pooling over all the elements there. And what we're proposing is to add multiple classifiers along the way. So layer 0 would not only feed layer 1, but it will also feed a classifier in addition that, again, does some pooling on the elements of layer 1. And then once this classifier is fixed, and we train all of these classifiers together, and then when we run an example, we can stop at the first layer, run this classifier, get its prediction. Again, prediction is I mean, we just compute the softmax and do some calibration and get a number that tells us how confident, quote unquote, is the model. And we use this as the decision whether to exit or to continue to the next layers. Okay,
so in this case, if I understand this correctly, you have multiple classifiers at each of the layers.
Exactly. And not each of the layers, but a subset of the layers. But yeah, you could do on each of the layers as well.
Right. Okay. And what is the overhead of introducing a classifier on top of kind of regular layers in that network?
Yeah, that's another great question. So one of the appealing properties of this method is that it produces very little overhead, because classifiers I mean, we experimented with BERT large, which is a model that has 350 million parameters, and each of the classifiers has a few thousand parameters. So roughly less than 0.1% if I got the numbers right.
Yes.
So very small overhead in terms of a number of parameters, and accordingly also a small overhead in terms of training. I mean, we train all of these together, but again, it doesn't cost much to run this classifier. So basically, the price is the same as taking the full model with just a single classifier on top.
Nope. Thank you very much. That's really cool.
Thank you.
Yeah, no, that's cool. I think we've got time for one more quick question. If someone wants, oh, there's a hand up. Where did it go? Oh, it's gone again. Damien's is gone. So I'm kind of interested in this early exit idea, and you're talking about kind of easy and hard models. I mean, there are seldom free lunches, I guess. If something is easier to converge, do you think you end up with a less resilient model when it comes to inference time, or does the data suggest that actually the models are good and you're just wasting time on extra compute?
Yeah, thank you. I really like this question. So I've been thinking a lot about, I mean, I think the next project that I've presented also touches on a very different angle of the same question of what is easy and what is hard. And I think I started this with the intuition that, I was having lunch with a friend, and kind of someone was saying something in the background, and kind of I got it even without, I was very invested in the conversation that we had, but I was still able to process the thing that someone was saying. Maybe they said, pass the salt or something. I mean, and you just pass the salt, you don't need to really focus on it, right? So this is the intuition that I had. I mean, why are we running our most expensive models on each and every instance? Some of them clearly we could do without the most expensive models. And I think that the key idea that, I mean, we're exploiting here is that the confidence level of the lower architectures, the lower classifiers, is to some extent accurate on how well they could handle it. And we indeed see a very significant speed up, again, up to a factor of 5, with losing maybe 1 point of accuracy at most. But I totally agree that, I mean, it's not trivial to make this prediction of, I mean, for a model to know whether it can solve this given instance or not. And we obviously do lose something by taking this route. And one of my students is currently working on ways to make this decision-making more accurate. Basically allow models to more accurately decide whether they're confident enough and they can make their early exit, or they should move on to the next one. But yeah, I totally agree. There is no free lunch in this sense that, I mean, we can just, if we had an oracle that tells us exactly which instances each layer could solve, we would be very happy, but this is far from being trivial. I hope this answers your question. I'm not sure.
Oh yeah, no, that's spot on. I mean, I think even if people don't care as much about the environmental impacts, the sort of disclosure of how much redundant work you're doing, or how when's good enough, and better application of the right size model to right size data, and I like your disclosure stuff as well about the comparing models, not just cherry picking the best result, but so there's some stuff about just better science here, isn't there, and better application of machine learning as well as that. So yeah, no, fantastic. Thank you very much for your talk. I really enjoyed that. That's all the time for questions we've got at the moment. So if you could unshare your screen, Roy, we'll get Loic queued up. Oh God, I saw my face there flash up. That was truly terrifying.
Alarming.
Yeah. Yeah. I don't think I'm getting more handsome with age.
Oh, I don't know. I don't know.
Oh, Julia, you're so sweet. Right. So, look, do you want to share your screen, and I'll give you the full time. And I apologize to people if we run a couple of minutes over, but I'm sure it'll be worth it.
Okay. Can you see?
Can you see
it?
Ideal. Damien, do you want to lower your hand? Right. Please start when you're ready.
Ideal. Well, good afternoon, everyone. Thank you for the invitation to talk here. I'm especially in great company, so really happy to have the opportunity to discuss green computing. Full disclosure, my background is machine learning, even though I'm kind of lost in the clinical school in Cambridge. That took a wrong turn. So hopefully we all talk the same language. I'll kind of take a step back from Roy's talk and just address the carbon footprint of computing in general, and not so dive in like the specificities of AI. But basically, I'll try to address three main questions. What's the sustainability issue of high performance computing? Then is green computing easy? Hopefully, I'll show you that, yeah, it can be. And then, but is green computing easy enough? And that's the part I'm not so sure about. So I've developed some of these ideas because I won't have time to cover everything, but in a kind of a blog article for BCS IT Now. So if you're interested, feel free to check it out. But the main idea is high performance computing. It feels a bit like magic. You have like dozens of CPUs, unlimited memory, everything at your fingertip. Just by logging in from a tablet or even a smartphone. Sometimes I can check on where my jobs are just from my smartphone, and that does feel a bit like magic. And on the plus side, it enabled a lot of great stuff. Like the first image of a black hole 55 million light years away, or huge progress in our understanding of proteins, for example, with AlphaFold from DeepMind. On the flip side, air pollution represents around 4.2 million deaths per year, and that affects 91% of the world population, according to the World Health Organization. And data centers, we all know that, need a lot of energy to run and therefore contribute to air pollution. There are lots of numbers around the carbon footprint of data centers, and it's really hard to estimate depending on what you include. But there's one number there's one number I find striking. It's basically as much as the entire American commercial aviation, and we do know how much they love their planes over there. So it is a huge impact. I'm sure it's a surprise to no one. So the next question is, why isn't there like a widespread concern in the computing community around that? And I chatted about that when we first released the Green Algorithm project with Victoria Cordes, and here are a few ideas I have. First, because I think emissions are a lot more abstract, compared to like the smoke coming out of a car. It's not quite so clear why running computation has a carbon footprint. Then there's the fact that fridges, dishwashers, TV, cars, all these devices, they promote their low energy needs and sustainability. And claiming or claiming to be sustainable is a key element of advertising campaigns today, and it's often a legal requirement as well. It's not the case for computers. Then there's something especially, I guess, for us in academia, is that computing time is virtually free for a lot of us. We have access to these large institutional servers, and yeah, we just there are powerful computers, and we don't really see the electricity bill at the end of the month. And something, yeah, I'm definitely guilty of. It just feels like we have unlimited computing power. And even for scientists who would like to do the calculation and find out their carbon footprint, until recently it was really hard to do it. So you had to like deep dive into the different components, and that's not a surprise that it's been ignored. And I guess the last point I would add, reflecting on some reactions we received when we first started to release that, and when talking, is institutional frictions. Not everyone is very happy about people looking into it, or even convinced that it's a problem worth investigating. A lot of institutions or funding bodies or journals don't really see the problem. So yeah, I guess that's maybe why we don't care so much about it. Obviously, and Royce talked about it, and there's been lots of talk about that. Deep learning is a particular problem because language models start to grow completely really big. That was an example of the it was the latest, I'm not sure it's the latest anymore, but one of the latest chatbot from Google, and it takes a month on thousands of computing cores to train, and that was the trend Roy was pointing at. And basically this really started to highlight the energy need, something we couldn't really see before. You may have come across this article from Emma Struble, which is perhaps the first time the energy consumption of deep learning models was actually measured and estimated. So it got picked up by a lot of media, and yeah, it's really interesting work. And yeah, they show that these large language models can have a very bad impact. And that drove the field a bit, and so a lot of other work. You will recognize Roy's article here, Green AI, and a few other work. There's the sustainability issue alongside like accessibility and ethics. I won't discuss it much more about that, but you know, one thing that relates to sustainability is the fact that the population suffering most from climate change and the environmental cost of AI, they are also the population benefiting the least from innovations such as Apple's Siri or Amazon's Alexa. And there's obviously the ethical challenges if large tech companies are the only ones controlling large language models that nowadays will underpin many aspects of society. That is obviously a problem. And actually, almost to illustrate this point, Google's disbanded the ethical AI team who participated in publishing the stochastic parrot article just before they released it. So not sure it's very reassuring. But there was some calculators on how to calculate AI, the carbon footprint of AI models, but that was very much for deep learning. So, you know, you could only look at models run using GPUs on cloud computing, so AWS or Google Cloud Platform, and that was it. So we started looking at it, and we're like, surely that's not only AI. In my department, we're doing a lot of computational biology. So we thought maybe AI is just one small part, and it is. So this is an interesting example. So XSEED is a network of supercomputers in American institutions, and they mutualize resources. It's basically a bunch of universities putting together their HPC clusters, so you know they can spread out the workload a bit better. And they have statistics. And last year, 9 billion compute hours were charged. That's 24 million compute hours every calendar day. I just find this number mind-blowing. And you can see on the pie chart, it's really spread out between all fields of science. And I can imagine AI kind of sprinkles around each field. But yeah, so that is a problem. And that is a problem across all fields of science, not only deep learning. Astronomy has looked at it, and that's really interesting. A lot of work coming from Australia. And they estimate, for example, that an astronomer has a carbon footprint significantly greater than the average Australian, and 5 times higher than the global average. What actually motivated our whole work was that. So we were wondering what's the impact of computational biology. So we did that. We basically surveyed the field and tried to benchmark the carbon footprint of a lot of tools. The preprint was released last year, but the paper just got out last week in MBE. So if you're interested, so work led by Jason Greeley from Melbourne. Okay, I'll talk about Bitcoin quickly because every time I remove this slide from my deck, and every time I have a question about it, so I've decided to just leave it for good. Well, Bitcoin is bad. I guess that's a surprise to no one. I guess the next question is, if you put it in comparison with the actual benefit for society, the trade-off is probably even worse. As a country, it would rank 27th in terms of energy usage, so it's ahead of countries like Ukraine and Norway. Perhaps more importantly, you could power all the British tea kettles for 28 years. Or the University of Cambridge for over 900 years, which is interesting because the University of Cambridge has only been around for 800 years. So we could like kind of double up again and still be fine. All right. So we do have a problem. I think I'm sure none of you doubted it, but I think it's clear now. We do have a sustainability problem with high performance computing. I guess the question is, where does this problem come from in particular? So I think we can broadly divide it into three main aspects. The first one would be the life cycle footprint. So by life cycle, I mean production, usage, and disposal. So it's usually called cradle to grave carbon footprint. For consumer devices, your iPhone, a tablet, a laptop, a phone, it's 70 to 80% of this total carbon footprint is only from production, which means just using your device for longer is the single best thing you can do to limit its impact. Charging the device every other day, or switching it off instead of letting it sleep, won't make much of a difference compared to actually not producing a new one. This number is a bit lower if we look at the hardware in data centers, because obviously they used a lot more because they're kind of almost in continuous usage, but it's still 10 to 20%, so quite significant. What's interesting is you've probably seen, when data centers will renew hardware, invest in new chips or new GPUs, they will usually do it because the warranty wears off, so it's not financially profitable to keep the hardware. Well, it would be interesting if sustainability would be included in that trade-off as well. Then there's long-term storage. So all these hard drives, obviously a hard drive doesn't use as much power as a CPU. But if we break down the energy bill of a data center, we get something roughly like that. So 50% for the servers, 10% for storage, and 40% for overheads for the average data center. And so that's still quite a large number if we take the total energy bill of all the data centers. And so storage does have an impact, much smaller, but we store things for longer. It's hard to give a number, but because it fluctuates a lot. It depends on the hardware, but as a order of magnitude, we can imagine that the cradle to grave impact is around 10 kilograms of CO2 per terabyte per year. So I mean, it's an easy fix, really. Just trying not to you store data we don't need, especially imaging data and things like that. Okay, so now we get to the heart of the problem, which is probably the part you've heard about the most, is the cost of actually running an algorithm, training an algorithm, the powering the computers during that time. So what to take into account? Which computers? There are lots of questions about that. Then we dive into different components. What parts are actually relevant? What part can we ignore? And what about producing the electricity? So basically each of these little points is a very deep rabbit hole you can spend years researching, especially if, and that's the case for most of us, sustainability is not our primary field of expertise. So that's why it takes a lot of time to find information about that, and that explains why most teams just can't spend the time finding out about it. I'll keep it quite high level today, but in summary, to find it, it only depends on two things, which is how much energy you need to put in the computer to make it work, and how was the energy produced in the first place. The quantity of energy just depends on the efficiency of the algorithm and the hardware, and how the energy was produced. It depends on the geographic location of the server. So usually the the energy mix of the country. I'll just pop in the equation here, but I won't go into details. Feel free to check out the paper if you're interested. But basically, that's just how we find the energy needed. It's no big surprise here, how many processing cores, the memory, and things like that, and the efficiency of the data center. What's also quite interesting is well, the carbon footprint of producing electricity, it's called carbon intensity, and it varies greatly between countries. So, for example, running exactly the same tool in Australia compared to Switzerland, so doing exactly the same task, it will emit a baffling 74 times more carbon dioxide for just exactly the same work. So that shows that if you want to look up the carbon footprint or the carbon intensity of a particular country, you can use electricity map. The countries in great change over time, so it's not always the same way. It depends on the data they have live. But that's why choosing the, when possible, choosing where the computations are done does have a very big impact, and perhaps the bigger impact, because it's like orders of magnitudes on the carbon footprint. Okay, so it's actually not that hard, but it's still quite a lot of work to find the information about everything. So we did lack kind of a standardized framework to estimate the carbon footprint of computation. There are frameworks to estimate the carbon footprint of specific tasks, but usually they are very detailed frameworks, which is good, but just not very easy to use. And actually, we were thinking, okay, well, the method is great, and we scientists, we love frameworks, but actually what we need is more of a tool, something that just makes it easy for scientists to calculate it. And basically, that's how it all started. We just said, okay, what's the impact of computational biology? Because that's what we did. And there was nothing. So then we had to do the work ourselves and find the information and everything. And we're like, well, that's silly that there's just no way for anyone not doing pure deep learning to know what the impact of their work is. So we created one. So we call that the Green Algorithms app. Feel free to check it out. It's a very simple online calculator, really. It's just you can input the details about your computation, how long it runs for, the memory usage, how many cores, what type of cores, where are you located, everything, and it pops you it gives you back the results. So how much energy is used, the carbon footprint of it, some context to better put it into context, and that's that's quite interesting. So there, if you check out the website, there are a bit more detailed. If you scroll down, there are explanations on how it works and things like that. So that was quite interesting. So we the first version of the app went live back in March 2020, and since then, over 3,000, 5,000 now, I guess, have visited the website, and it's from all over the world. So it seems to confirm what we thought, which is that scientists do want to be mindful of their own footprint. They just needed the right tool to do it. And I think now we're about like 150 users a week on average, which is great. A legitimate question is, does it work? Is it accurate? Because obviously we have to make assumptions. We have to simplify some aspects of it. So is it just too easy to have a calculator like that, or does it actually work? Well, to go back to Google, I hate to pile on them, but they kind of don't help me. They're not quite happy with the concerns being raised about the environmental cost of AI models. So they decided to release an article promoting how sustainable NLP is in general. And I'm not going to dive into the paper in details here, but what interests us is this figure, because they actually benchmarked our tool, because it's easy for them to do, because they have the data center, so they have access to the actual physical machine, and they can easily plug in a device to it and see how much energy goes through it. So they can actually do measurement compared to the estimations. And they compared it to the red bars are another calculator, the ML calculator, which is only for deep learning, and the green bars are Green Algorithms project. So these are only deep learning projects because it's Google, and they wanted to show that NLP is great. So two things worth noting. The first thing is, for all these ones, it works actually really well. I was surprised. I was expecting the errors to be a bit bigger, because I assumed, it is an estimation, and we knew it would be an estimation. We just decided it had to be usable rather than being super accurate. And so it's actually really close to 1. We want the ratio to be close to 1, and that was great to see. And then, yeah, obviously there are these bars that are like standing out, and for that it's not quite so good. But if you look at what the chips are, they're all using Google's TPUs. So if you don't know, these are specific GPUs. So they're basically graphical chips made specifically for deep learning, and only Google have them, which means we actually have no information about their power consumption. So normally the power usage of a chip is made publicly available because anyone putting it in their laptop or their desktop computer needs to know how much power it needs. But Google doesn't because they don't sell them. So that just shows that transparency is key. If we had the information, our estimations probably would be just as accurate. It's just they don't share the information, so it's not. So yeah, was quite happy with this figure. So in summary, when we have the information, and the vast majority of us are working on commercial processors, GPUs like the V100 or the P100 and things like that. So overall, quite positive. I guess the only thing, it's actually just came out yesterday, so I just added it last minute, but they released a new article saying how, being very optimistic about how the carbon footprint of machine learning will just disappear somehow. It will plateau and shrink is their quote. I think I'll remain skeptical for a little bit until proven otherwise, but at least they're pushing it. Okay, so very quickly, a few interesting things we learned along the way. More cores or more GPUs, not always better. So I guess the key argument is, saving 10 minutes on the runtime, is it worth the carbon footprint? Memory usage matters, and we've all done it. Just over-allocate memory, like say, oh, I need 50 gigs. Let's just allocate 100 because I don't want it to crash in 2 hours. So let's just be safe. As we've just seen, the information for informed decisions is often missing, and offsetting. So when you buy carbon credits, which is what Google does and what all the large cloud companies do so far, even though they're tending towards generating green energy, but not quite there yet, is a good option, but it should be really a last resort because it's really hard to make sure that what you're investing in will actually offset the right amount of energy, and it's usually best to reduce as much as possible and then eventually offset what's left. What can we do about it? Well, it turns out there's a lot. I pointed at some of the things already. Roy's listed especially in machine learning, a lot of great ways to limit the impact. I won't have time today to go through all of that. We're a bit short on time, but if you're interested, we published a quick 10 simple rules article. Well, it's basically for any computational scientist, so we just list easy ways. We worked on that with Alex Bateman from Embody BI. So hopefully that can be useful. What do we still need to do? I think we still need to reduce frictions further, because that's the problem. If it's a little bit hard to estimate and acknowledge carbon emissions, people don't do it, and that's understandable. So we need to make it even easier. And we need transparency from everyone, obviously from hardware manufacturers. We've seen how important it is. From data centers, not only cloud, but also institutional data centers. We've had some pushbacks sometimes when we just sent an email saying, what's the efficiency of your data center? It's just a number, basically called the PUE, tells you how much overhead is used. Sometimes we had quite a strong pushback against that. From institutions in general saying, okay, you're running computations in Cambridge, this is the efficiency of the data center, this is where it gets its energy from, this is the carbon footprint. And from us, obviously, we all need to be a bit more transparent about what we do, and to just acknowledge, it's the first step, just acknowledge the carbon footprint. I guess the main thing here is very much not to say we shouldn't do computation. It would put me out of a job, really, but it's just saying you would never start a wet lab experiment without having a bill at without knowing how much it will cost you. So it's the same thing here. Okay, very quickly about removing frictions further. The app is great, but it's still, you have to input numbers and find numbers there. So instead, I was like, okay, how can I make it easier? And I thought having something like that would be great. You just type it in your command line if you're working on a HPC server, so you're just interacting with it. And I just thought, oh, if I could just have a command where I say my carbon footprint, and it gives me the carbon footprint for the year or for the last month. So I did it. So it's very much a beta version. It's not ready at all, but yeah. So basically, it gives you all the information you need. It is arguably a lot less pretty than the app, but the information is here, and it's actually a lot more accurate because it's pulling your logs from the workload manager. So yeah, if you want to get involved with that, it's still beta version. It's all on GitHub. But if you would like to try it out on your system, there's no it doesn't do anything. It's basically just Slurm commands and that's it. So no permissions or anything is needed. But yeah, if you want to try it out, I've been trying it on CSD3, the data center we have in Cambridge. But if you want to try it out, do reach out. I'd be really interested in seeing how it works in different places. And yeah, transparency. That's what we try to do. So we now in our lab we put like carbon footprint statement at the end of our papers. So we just estimate it, and then we just publish what's the carbon footprint of the work, and we try the part we can't reduce, we try to offset it. And as you can see, we usually offset many times more than the carbon footprint, just because we know that offsetting is a bit of a complicated topic. All right, just on time, so I'll leave it there. I just want to thank everyone who's been working on that. Jason Goody's been leading some of the work, Michael Inouye, Alex Bateman from EBI, and all the funding bodies. So yeah, if you're interested, I usually post updates when I update the app and things like that. I usually post that on Twitter or just reach out by email. Yeah, and I'm happy to take any questions. Thank you.
Fantastic. I mean, you were like 4 seconds under time or something. I mean, that was absolutely spot on. Fascinating stuff. So the same rules as before. If people have questions, just pop your hand up or post in the chat. I think Petter, you were fastest finger first. Do you want to come in?
Yeah. Hi. Thanks for a very interesting talk. It's very much my research, so it was very interesting to hear about. One thing that I thought is sort of missing from the tool, or at least from the formula you had in one of the slides, is heat reuse or waste heat reuse. So in the Nordics, for example, we use it to heat buildings, dry wooden pellets, and so on, which means that the carbon footprint would be different.
Sorry, I just cut off here. Sorry, what was missing?
Waste heat reuse. So, all the ingoing energy to the servers become waste heat. And so if it's reused, you end up with other figures and other sort of sustainability footprint. And another thing is that PUE, which you mentioned, says nothing about, and this is, I think, interesting for both talks today, because it says nothing about the efficiency of the computation. So in fact, the less efficient the server is, or the less efficient computation, the better the PUE.
Well, the PUE just depends on it's very much the server. So regardless of what you're running on what you're actually running on the servers, it just tells you how much it needs, how much extra power is needed in total for overhead.
It does, and that's exactly the point. So if you have old servers, for example, which are not very energy efficient, then the PUE will get better. Because more than if you have new servers, because more of the ingoing energy is needed for servers instead of for overhead as cooling, for example. But great talk, and it would be nice to look up more on what you've done, and maybe to come down to Cambridge. We're working on new energy metrics in our lab, so it would be very interesting to hear more. Thank you.
We'd be happy to hear about that.
Yeah, thanks.
Thanks, Petter. I'm going to keep an eye out for other hands up. Who else have we got? Right. While I'm looking for that, so I think I know the answer to this, but I was interested with the XE cluster. Clearly the data disclosure let you do something that otherwise only the sort of closed actors like Google can do, right? Because it's a sort of inside or outside problem. And in terms of sort of transparency and disclosure, what do you think? You would argue that there should be much more disclosure, and what should they be disclosing in an ideal world to make green algorithms more accurate?
Well, I think what's really important, I'm not pushing for like full disclosure, just from like until just tomorrow. That's not going to happen. If at least institutions disclose information to their own researchers, that'd be a good start. Because when I ask people, do you know what's the PUE? So do you know what's the efficiency of the data center you are using? Most people don't know. And some institutions, if you email the data set, I mean, Cambridge has been great, to be honest. I should say that, because I emailed them, said, what's the PUE? And they sent me the PUE. They said, that's it. But if it would be on, even if it's an internal page because they don't want it to be made public, that's fair enough for now. Why not? But at least people doing the computation should have access to this information. What's the exact hardware being used? What's the efficiency of it? Cloud computing don't release that. They release the PUE, but it's very aggregated usually. So you don't know what's the efficiency of the actual data center you're using. Amazon's terrible for it. There's just no data. They will put one number, which is the average, including Iceland, where obviously you don't need to cool anything. You just open the window. So yeah, transparency for that. Then I think it's just up to, for now, it's just up to any scientist. If teams don't want to release their carbon footprint, I think it's maybe a mistake, but I can understand that sometimes there can be massive pushback or it can be complicated. I mean, there are probably lots of like PR problems because, you need to, if you release that, you need to convince the public that, the outcome of your research is also as valuable as the carbon footprint, and I can understand it can be an argument that can be difficult to make in some cases. But scientists who want to acknowledge it should be able to do it.
I think that's kind of fascinating because both of you are sort of arguing for a change of practice in a way that, I mean, presumably there are powerful actors here. So for academia, they would probably be, the journals could start to mandate some honest disclosure of AI to not to the distribution thing of ROIs and some, carbon footprint estimations.
No, that's a really good point, because just thought I mentioned that there's a team in UCL working on that, but that's a point we've been making, which is when you publish in a medical journal, you need to say, I got ethical approval for all the studies, and you have this ethical. And we thought, well, actually, the same thing could be done for carbon footprint. And indeed, that's exactly what you're saying. Grant, like funding bodies and journals could do a lot for that, saying, we're not considering it if you don't put this form at the end of your paper. Well, everyone would be doing it all of a sudden. But there are teams in UCL working on King's College London and UCL working on that, which is quite interesting.
Okay, no, that sounds really good. I'm just as a total randomer, I'm reviewing a paper at the moment which is talking about financial risk disclosure, and you can imagine. I bet none of the impact of the day-to-day business that these businesses are having on the environment is properly accounted for to their investors. And I can see a message from Roy that it's going to have to run. Cool.
I think there's a hand up.
Right, let me go looking for that. Thank you.
Yeah.
King Feng.
Hi there. Great talk. So I'm just wondering, is related to the use of your green algorithm. So say, for example, I have an algorithm. I know using your calculator, I predicted a runtime of this algorithm, and I use your green algorithm to calculate the usage. Have you thought about any future work to extend onto, like, based on the energy calculated, I can re-optimize my algorithm? Is there any work has been done using like your app?
That's a really good point, and that's something I guess is difficult because it's a change of practice. But something simple like sometimes you're trying to merge two large data frames and it's a bit of a hassle. So you say, oh, I'll just be lazy. I'll just take 200 gigabytes of memory and just do like a quick and dirty merge. It will take me 10 minutes and that's it. Or I will spend the next 2 hours finding a smart way to filter rows out first. And I guess in this case, if you were to estimate it beforehand, obviously for much bigger projects, but you could be like, well, actually the difference is not that big. Let's not waste time on it. Or actually the difference is big. Let's spend the extra time to optimize it. And I would hope that, if people estimate it beforehand, they will put a bit more thoughts. I guess it's hard to push it. All I can do is to kind of give the calculator and like give the option to people to estimate it so they can decide it beforehand. But yeah, no, I mean that's a really good point.
Yeah, because I guess like it is important in the world of like tiny ML, like working out how much your algorithm is going to consume energy in IoT scenario for like a lot of inference at the edge. So yeah, I just thought like it'd be interesting just to hear your thoughts on it.
Yeah, no, it's
Cool.
it's really important.
That's a good question. I just had a sudden mental image of the paperclip pops up. It looks like you're about to train a large model. Do you want to?
Yeah.
But you can imagine it, like dry runs of the tools or things giving you, this is what we think the estimate's going to be. So people could more easily test stuff. Yeah.
It could be integrated. We can't do it ourselves, but it could be integrated in stuff like TREs, so trusted research environments, where people do research on, because when you submit the job, you could have like a confirmation window or Slurm. I don't know if you use Slurm, but basically, you just it's just a workload manager that handles the thing on the HPC cluster, and you submit your job. But when you submit your job, you say for how long you want it, and obviously the thing knows what the chips are and what the processors are. So actually, it could have an upper limit of the carbon footprint. It probably will be less because it probably won't run for the full time, but you at least have an upper limit there. So it could say, put a display message saying, this is how much it will cost you. Are you sure you want to continue or something? But so there would be option, but it requires a lot of third parties to join the movement. But we're hoping that it will get to that.
Yeah, no, that was absolutely fantastic. Great pair of talks. Thank you so much for joining us, Loic. It's appreciate you doing that. And thank you everybody for your patience. We did run over, and that was my fault for asking questions and that kind of stuff. So I think we'll call it there.
We do like to invite people to unmute and just do a very short round of applause.
Oh, marvellous. Let's do that then.
So thank you very much for your talk.
Yeah. We'll have to record that and send it to Roy because he had to leave.
Yes, exactly. You missed out on his round of applause.
All right. Thanks everyone. So yeah, please do check out this work. And obviously Green Algorithms is up and the code's on GitHub, so there's potential to actually get involved. And I really like the good practice of declaring the impact of the work in the papers. I think that's exemplary, and I hope to see many more researchers doing that. So fantastic. Thank you. Thank you
for the invite.
Great pleasure.
Thank you very much.
Have a good day, everyone.
Thank you. Bye. Bye.
Bye.